Thank you very much, Falco, for your warm words. And of course, I would like also to thank the organizers of this event, especially Stéphane Bazir, who invited me to talk to you today. Actually, I must say, after the first event of E2I Talks in June last year, I thought to myself, wow, that's a pretty cool event, and would be very nice to also participate one day and present your topic. So today, I would not say that the dream came true, but I'm very, very honored, and it's a huge pleasure for me to talk to you. So my contribution, as already mentioned, presents the academic part of this event. So I was told by the organizers to proceed in a more didactical way, let's say, to explain the things. So feel free afterwards to tell me if my explanations were clear enough, or if I managed to completely confuse you. Yeah, all feedback is welcome. So I would like to talk to you about photoelectrochemical approaches for energy storage, namely fuels which can be produced directly by using sunlight energy, and how we can use these fuels to store large amounts of energy. My talk will be structured as follows. I will give a short introduction to the energy challenge we are currently facing and deduce why energy storage is absolutely necessary, and also deduce why solar fuels can be attractive candidates for future energy storage concepts. Subsequently, I will present how these solar fuels can be produced, and will focus mainly on two photoelectrochemical processes, namely the solar water splitting process and the solar CO2 recycling. And for both technologies, I will also share with you the latest results, the latest advances, and also show how we can, from a pure academic research result, transform this to an industry level, and by this, bridging the gap between pure innovation and commercialization. So I believe we all agree on the fact that the ever-increasing world population causes severe energy concerns. In particular, the increasing energy demand causes alarming depletion of natural resources, and which in turn then also produce a lot of emissions, greenhouse gas emissions, in particular CO2, which can even have more detrimental effects in the future. Direct consequences. The consequence of these emissions is global warming, with very drastic consequences for the environment and for the climate. So in order to provide a very healthy and sustainable future, we absolutely need to draw on renewable and clean energies in the future, which preferably are abundant and available at large scale. So here I plot the world consumption for this year, which is projected to reach, in the year 2050, 28 terawatt per year. Nowadays, more than 80% of this energy need is met by finite energy sources, such as fossil fuels or uranium. And as already mentioned, these finite energy resources are, however, depleted at an ever-increasing rate that the planet, in the long term, cannot sustain. Therefore, it is absolutely we need to draw on renewable energy sources. Here we can, for instance, use geothermal energy, hydrothermal energy, biomass, or wind energy. However, when looking at the provided power, there's one obvious choice for the energy source of the future, which is the sun. So the sun provides per year 23,000 terawatt in power, which is way more than we use annually. And just to put this in some kind of a perspective, the sun provides on Earth the same amount of energy in 1 year that the entire planet uses in one year. So in 1 hour, the sun produces as much energy as we consume in 1 year. And I think this is an amazing fact. And for me, as a researcher, this was always a huge motivation to continue research in this topic. So, solar energy must be the renewable energy source of the future. However, of course, with sunlight energy, there's one big issue. I guess you know what I'm referring at. When there's no sunshine, you have no energy. So In this case, really the storage is the challenge. We need to store this solar energy for the time when there's no sunshine. How can solar energy be stored? Of course, we all know solar cells, where the solar energy is converted into electricity, and then this electricity in a subsequent step can be stored in batteries, for instance. Another storage concept is the solar thermal energy storage concept, where solar energy is stored in heat in the form of heated water tanks, for instance. However, the storage concept which I will focus today is photoelectrochemical energy storage. Yeah, here, the solar energy is directly converted into chemical energy in the form of so-called chemical fuels, so-called solar fuels. Here we can name, for instance, hydrogen as possible fuel, but there are way more, as we will see in the following of the talk, when we use, for instance, not only water, but also CO2. There's a wide range of products we can gain from this photoelectrochemical energy conversion. But why are solar fuels important, not only for academia, but also for industry? So for this, let's have a look at the facts. So as already mentioned, in the future, we need to store the solar energy on a terawatt scale. And in this regard, the energy and power densities of synthetic chemical fuels, so solar fuels, are hard to beat. If you have a look at this graph, which plots the energy storage duration and power of several storage technologies, you see that if we want to store a lot amount of energy over a prolonged period of time, you see that the chemical fuels, for instance, hydrogen and other candidates, outperform most of the other energy storage technologies like batteries or supercaps. In fact, solar fuels all possess very advantageous characteristics as being used as a fuel. So the high gravimetric energy density, just to give an example, 1 kilogram of hydrogen, for instance, can store 3 times more energy than 1 kilogram of gasoline, for instance. It is environmentally friendly, so when used in a fuel cell car, for instance, you don't have emissions of carbon dioxide. This car only emits water. Yeah, so it's very environmentally benign. A very important point is then that it can be produced by using renewable energies, so as solar energy, and therefore it's not dependent on fossil fuels, which is a crucial criteria for future energy storage concepts. So coming back to our energy challenge to-do list, we can say that solar energy can be stored very efficiently by using chemical fuels. So now the question is, how can we produce these chemical fuels? And for this, we don't have to reinvent the wheel. We can just look what nature has been doing over the past 2 billion years in natural photosynthesis. So plants use water, CO2, and light to produce oxygen and sugar. What we try to do in the laboratory, so in the research field, is to do a kind of artificial photosynthesis. And in such an artificial leaf, as depicted here, we use sunlight energy and water to split the water and get out oxygen and hydrogen. And in this case, hydrogen would be our energy carrier to store the energy. This process would be called solar water splitting. If we additionally would let in CO2 here, you see that besides the hydrogen, we can even get more value-added products, namely CO, methane, methanol, and as we will see in the following of the talk, even much more value-added products. And this process would then be called solar CO2 recycling. So now that we know how to produce these solar fuels, the question still remains, how can we make available this technology for everyone? So, and for this, the major driver will be cost. Yeah, so you have to make this really, really cheap, and in order to make this cheap, the choice of the material and processing must be very cheap. And we at IREC here in Barcelona, we choose only earth-abundant and cheap materials. As we will see in the following, these can be silicon, zinc, or copper, and for this, really ensuring an availability with very cheap materials. So how would this process look in a practical way? So I want to show you now the photoelectrochemical process in more detail, and we'll start with the solar water splitting for then afterwards explain the CO2 recycling. So in praxis, this would look like this. Here I schematically depicted a standard electrolysis cell, so an electrochemical cell with its components, metal anode to do the water oxidation and to form oxygen, a metal cathode to do the reduction of the hydrogen cations and form the hydrogen. Both electrodes are separated by an electrolyte and connected to an external power supply. And this external power supply then delivers the power in order to drive both water splitting reactions, namely the oxygen formation and the hydrogen formation. Our aim, however, is to power the system without any external power supply, just by using sunlight. So therefore, we want to get rid of an external power supply and replace one of both electrodes by a solar cell. Yeah, as shown here, and exactly this configuration corresponds to the photograph we just saw. So we have a photo-absorbing material here in red, which is separated to an electrolyte to a metallic anode at the other side. Under illumination, this device, this photocathode solar cell produces a certain photovoltage. And in order to drive the system now without external bias, just by using sunlight energy, this photovoltage must be higher than a so-called thermodynamic reaction potential defined here to really split the water into oxygen and hydrogen. This reaction can be accelerated or facilitated by adding catalyst materials here at the solid electrolyte interfaces. And you see that actually this device is a complex device. You have on one side the solar cell, which has to be adapted, or the photovoltage of this solar cell has to be adapted exactly to the need of the electrochemical reaction. And of course, this solid electrolyte, solid liquid interfaces play a major role. Actually, they have a twofold role. As already mentioned, the catalyst layer here should enhance or accelerate the chemical reactions in the electrolyte, but they should also protect the device from this electrolyte, so protect from corrosion or oxidation. Just to give you a concrete example under real operating conditions, so actually this device configuration corresponds to the same we just saw. Here we designed a specially adapted triple junction solar cells. You see we have 3 different absorbing layers. And for this configuration, we tested different catalyst materials for the hydrogen and for the oxygen evolution reaction. The catalysts we chose, they varied a lot in catalytic performance. So here, ruthenium oxide was the catalytic most active material, but unfortunately also, it's the most expensive material you can use for this application. So we started with the cheapest, most earth-abundant configuration, where we took nickel on the hydrogen side and cobalt oxide on the oxygen side, and we came up with this current voltage curve. We then went to nickel oxide, which showed already a slightly better behavior in terms of higher photocurrent density and higher photovoltage. Same trend we saw when taking iron oxide, and then the best performance was achieved by taking the most expensive materials for catalysts, namely platinum and ruthenium dioxide. Exactly, in terms of high photocurrent and high photovoltage. We then also modeled this device and could exhibit a nice agreement between experiment and then simulation, and so we could validate the measured, in this case, 7.7 milliamps per square centimeter value. This is really, here you see this value is measured at 0 volt, so there was no external power supply or power added to the system. In calculating this into a solar to hydrogen efficiency, we ended up with this 9.5% already mentioned by Falco. Just to put this a bit in context, industry long time set as a requirement that these integrated systems can be competitive with other technologies was always okay. You have to overcome the 9%, and with this proof of concept, we showed okay. Also with this technology, which is integrated, which can be applied delocalized, it can be flexibly adapted to the consumer needs. We can reach your requirement over 9%. Still, this was just a proof of concept. So the next step was then to think about approaches, engineering tasks, how to upscale the whole system. And this was also a study done in Jülich in Germany, and you see that this device is a quite complex device shown here, which includes a lot of lasering steps and different layers. But in the end, we ended up with a very upscaled device. Just to compare, the cell I showed you before with the 10%. At this size, and so we really managed to increase this integrated wireless water splitting device up to 64 square centimeter. Due to some constraints in the design, we ended up with a bit lower efficiency. Actually, I put a video. I hope it. Yeah. Exactly. Yeah. Thank you. So this is the device. Yeah, you see no wires, no external power supply. Here on the right, you produce hydrogen. Here on the left, oxygen. So yeah. To put the device here in grass was actually an idea by the photograph. I won't comment on this one. But you see, that's really going from a pure academic results on very low, small scale. We managed to upscale this whole integrated device and ending up with a nearly commercial device. So the next topic I want to present to you is the topic of solar CO2 recycling. So why is this important? So nowadays the consensus is that carbon dioxide capture and storage alone cannot solve the problem of the increased greenhouse gas emissions of CO2 emissions. So to have a meaningful effect, we need to materialize concepts and approaches to reuse, so to say, recycle the CO2. And this research is done in Barcelona at IRAC. So how would this process look like? In this case, CO2 and water would be the feedstock. And then in a process mimicking artificial photosynthesis and using catalysis, we would end up with value-added fuels. You see the carbon dioxide conversion or recycling. So the chemistry of this process is much more complicated than the pure water splitting. So you see that besides hydrogen, we can have a lot of products from these reactions. These are multi-step reactions which usually require even more energy than the water splitting reactions. However, among them, we can see that, for instance, the production of carbon monoxide only requires 2 electrons, which therefore also is accompanied by less losses than if you would go for reactions for methanol or methane, for instance, which require 6 or 8 electrons. Additionally, with the accompanied production of hydrogen, you can form the so-called synthesis gas, or also called syngas. And syngas offers you a high optionality for further processing to get fuels or chemicals. How would this look like? So in the CO2 recycling, Afterwards, you end up with a certain ratio, a hydrogen to CO ratio, and based on this ratio, you can further process by thermochemical processes, for instance, materials such as ammonia, methanol, or other oxo products. And so being able to provide a tunable hydrogen to CO ratio is quite alluring also for the petrochemical industry, for instance. Just have a look at the selectivity of several metals towards reduced products. If we're talking about syngas, of course, hydrogen and carbon monoxide is interesting. And here we can identify mainly three metals or three materials: gold, silver, and zinc. And in view of a commercial application at large scale, expensive materials such as silver and gold are not very adequate. Yeah? A more appropriate choice in this regard would be zinc, and it's also why we focused on this material. So in contrast to water splitting, as I told, the chemistry of CO2 conversion is much more complicated because also you have a liquid phase, the water, and a gaseous phase, namely the CO2. But basically, the catalyst can be deposited on two different kinds of electrodes, namely planar and gas diffusion electrodes. We see a gas diffusion electrode has kind of a three-dimensional structure, and the advantage of this gas diffusion electrodes is quite obvious. So in a planar electrode, you are limited on the geometric surface area, so your active chemically active surface area cannot be increased, whereas in a three-dimensional skeleton structure, you see that the active surface area is much higher or much larger than the geometrical surface area. Another important point is that mixing water with CO2, the CO2 solubility is quite low. So we have to find ways in order to circumvent these solubility limitations. And you see in a planar electrode, you have to let in the CO2 from the top, and then it has to travel a long way in order to reach all the chemically active surface area. Whereas in a three-dimensional skeleton structure, the CO2 can penetrate through the pores and therefore reach the catalytic active surface much easier. And that's actually exactly what we did at IRAC. So we took a three-dimensional copper foam, which we coated with zinc from a zinc sulfate solution, and we ended up with a kind of zinc flake structures, which even gave, in addition to the three-dimensional foam structure, even more highly active surface area. The electrochemical characterization I want to show here. Here I plotted the Faradaic efficiency over an applied voltage. Here the Faradaic efficiency, just to explain, gives you the efficiency of a charge with which a certain product is formed. So you see here we nearly reach 100% of products which were carbon monoxide and hydrogen, exactly what we desired. Yeah? The highest Faradaic efficiency for CO was 85% at this voltage with a very high yield. So we nearly reached 40 milliamps per square centimeter for this Faradaic efficiency. And when talking again about this hydrogen to CO ratio, we see that with this cathode we were able to exhibit a wide range of this ratio ranging from 5 to 0.5, and this is quite important in order to have a high flexibility in using this syngas mixture. So now having a very efficient and tunable cathode at hand, the next step was, of course, to integrate it in a real solar CO2 recycling device. The device we use is depicted here. It consists of a filter press cell. This cell has three inputs, namely catholyte, an anolyte, and pure CO2 gas. Both electrolytes are kept in two different compartments and separated by a membrane. The developed copper zinc cathode is mounted here in a holder. in this device, it had an area of 10 square centimeter. Actually, in this device configuration, this can be enlarged very easily. And on the other side, we had the silicon solar cells, electric connected to a nickel foam in order to promote the oxygen evolution reaction. The first test we did was to measure the device under dark conditions. We just connected the developed copper zinc cathode with the nickel foam and tested two different membrane configurations. We had a bipolar membrane configuration, the BPM, where we could use two different electrolytes, KOH and potassium bicarbonate, and we tested one Nafion membrane configurations where we used in both compartments the potassium bicarbonate. And as you can clearly see from this current voltage curve, that the bipolar membrane configuration outperformed the Nafion configuration by far. To have now an approximation how this device would work under illumination conditions, we can overlay this current voltage curves with a current voltage curve of the applied solar cells. You see here, using one silicon cells, it would provide a very high current but low voltage. In order to operate the system bias-free, one would have to work in this region. So we went to a series connection of two silicon cells, and you see that even there we this series connection didn't provide enough photovoltage. We had to go to a connection of 4 silicon cells in series in order to reach high enough photovoltage and to operate the device here in this region. And we ended up with an approximated operation current of 5 milliamps per square centimeter. We then also validated this, and indeed we could measure a bias-free, so without external power, a photocurrent of 5 milliamps per square centimeter over a prolonged time. I also measured the Faraday efficiency, which was 4.5, and calculating everything into each other, we ended up here with a solar to syngas efficiency of 4.3%. And this is one of the first and rare examples of an integrated device for solar CO2 recycling, and we managed to publish this in a very renowned journal, and this positioned our institute in the lead of the research in this topic. This efficiency is a bit lower than the solar water splitting efficiency we saw earlier, but so this technology is quite in its beginning still, but the trends in efficiency increase are the same as for water splitting, as I noticed 3 years ago. So this is also quite promising research topic. So just to conclude, I hope I could persuade you that solar fuels offer attractive pathways for future energy storage concepts, especially hydrogen and CO. So syngas could be versatile chemicals with high optionality. At IREC, we only use earth-abundant materials to achieve this fuel production, and of course, with prototyping and building demonstrators, we show that these devices not only are on an academic level, but we transform them to an industry level and show or demonstrate that this could be a business opportunity as well. With this, I'd like to close up, and it's one of my favorite quotes. So the best way to predict the future is just to create it. And with this, I'd like to thank our sponsors and, of course, you all for your very kind attention. Thank you.
Thank you very much, Felix. If I understood it right, although the 4.3%, it would be still by far sufficient efficiency to provide enough energy for the world.
So far I would not go, yeah, but it is on the way to reach this from industry set 9% for this integrated solution. Of course, you have solutions where you can have a PV farm outside and some electrolyzer somewhere else and then combine everything. But with this, we think we can save costs, can save money. There's no maintenance that much,
Yeah.
and as I said, you can use it delocalized. So this is applicable on cars already. So sure, the efficiencies. When we talk about efficiencies, we cannot really compete with other technologies, but we see potential. Yeah.
All right. Thank you very much. Thanks again, Felix.
Thank you.